Gee, I have no idea what this is. I guess I gotta use IR. Wait, I know what that is. That was amazing. IR is wonderful. It told me all this. I really wonder what goes on there. So if we really want to understand IR spectroscopy, we've got to review some basics. Remember that spectroscopy in general is the study of the interaction of atoms and molecules with electromagnetic radiation. And the key to all these different spectroscopic techniques that are out there is that depending on the wavelength of the incident radiation, atoms and molecules will undergo different physical processes. And each of these can tell us useful information about those structures of the atoms and molecules. IR spectroscopy in particular utilizes radiation from the infrared region of the spectrum. There's going to be a lot of math in the slides that follow, so we want to review some core concepts. Atoms and molecules are quantum mechanical systems. That means that they have their own wave functions. Remember that a wave function in quantum mechanics can tell you everything you need to know about that physical system that it's associated with. You just need to feed it to the appropriate operator. I've heard operators be described in the past as oracles. You give them a wave function and they give you back some information, particularly a measurement about that system's physical state. So for example, on the right, we have the time-independent Schrödinger equation. In green is the Hamiltonian operator, an energy operator, and in blue is the energy eigenvalue, which is a measurement of the energy associated with the wave function there in black.
This brings us to diatomic molecules. Diatomic molecules are the simplest class of compounds to use in quantum mechanics to predict the frequency of radiation that must be absorbed to cause a transition in vibrational state. These molecules can be mathematically described as oscillators, and in this oscillator model, the two atoms are treated as two masses, M1 and M2. And connecting these two masses together is a spring that has some sort of force constant, K, which represents the bond strength or bond stiffness. And since we are using a spring in this system, the system also has potential energy, and this is due to the displacement of our atoms being pushed together or pulled apart. Continuing, we have harmonic and anharmonic oscillators. A harmonic oscillator is when the plot of the potential energy is parabolic in shape, which means it is symmetric when cut in half from the equilibrium point, and anharmonic means it is not symmetric when cut in half from the equilibrium point. The total energy of our oscillator system is given by the sum of its kinetic energy and its potential energy, as seen here. The potential energy depends on which system we are using, either harmonic and anharmonic, as seen here, and the eigenvalues of this expression depend on our quantum number n. And n can be any number from 0, 1 to 2, and so on and so forth.
The difference between the energies of two states can be found with this equation, with n representing the quantum number. The result that you get represents the energy a molecule must absorb to execute a vibrational transition between those particular states, and this equation translates these energies into absorption frequencies. And so there's two types of vibrational transition: stretching, the change in distance between two atoms, and bending, the change in angle between two bonds. So these vibrations can be fundamental, the change to the next energy level, which is the harmonic oscillator. And overtone, the change is between many energy levels, which is closely related to the Morse oscillator or the anharmonic oscillator. So when a molecule absorbs a packet of energy, it undergoes a physical transition. It moves from a lower to a higher energy state. So once the molecule is in that excited state, the energy manifests as a continuous vibrational motion. The atoms move back and forth relative to each other at a characteristic frequency caused by IR radiation. So molecular vibrations aren't the transitions, but rather an option that's available to a molecule to do something with that packet of energy it's been given.
One important aspect of IR spectroscopy is the determination of a molecule's IR activity. As previously mentioned, vibrational frequencies exist as either bending or stretching motions. The detection of an IR active molecule only exists if the dipole moment of the molecule results in a net change during that vibration. To determine if a molecule exhibits a net dipole moment, we must determine the molecular point group associated with it. The point group represents the complete set of symmetry operations for each molecule and can be easily assigned once the molecular geometry is known. For example, carbon dioxide is a linear molecule and belongs to the d-infinity H point group. In contrast, sulfur dioxide is bent and exhibits C2V symmetry, where the highest rotational axis corresponds to a 180-degree rotation about the principal axis. This lower symmetry makes sulfur dioxide a polar molecule with a permanent dipole moment. On the left shows a symmetric stretch of CO2 being completely inactive, while a symmetric stretch of SO2 is IR active, which corresponds directly to the geometry of that molecule. Now, how do we interpret IR data? This figure shows an IR spectrum collected from an organic chemistry lab of salicylic acid, which is an important molecule in both medicine and cosmetics. Since salicylic acid is a small organic molecule with 3 distinct functional groups, we can use the IR stretching frequencies to identify them. A strong broad band can be seen from 3300 to 2500 wave numbers, representing the carboxylic acid group. While the alcohol has a similar stretching frequency, it is concealed by the carboxyl group. We can also identify the aromatic stretches of benzene at 1609 and 1481 wave number. One useful example of IR in the lab is the verification of an organic transformation. If you fully reduce the carboxyl group of salicylic acid to the corresponding alcohol, the carbonyl band that exists at 1615 wave number will actually disappear. IR spectroscopy is a widely used analytical technique in all areas of chemistry to identify specific functional groups and organic transformations.